Let's now calculate the moment of inertia of an area. Okay, so we'll start out by the differential form here. And depending on how you choose the x-axis or y-axis, it's going to vary, right? So this represents the moment of inertia of an area about the x-axis, and this is the moment of inertia about the y-axis here. Now, if we look at this differential element here, it's really talking about if we have the axis x here, it's really asking if we have a small differential element dA, a small bit of area, and the distance that it's acting away then is y. Okay, so it's y squared times this area. So to get a very big moment of inertia in terms of the x-axis, we're looking for the distance from the x-axis to be as far as possible, all right? Because there's a square term here. And that is part of the reason why an I-beam, for example, is such a good example of a high moment of inertia of an area. Because if we draw our x-axis right through the middle here, there's a lot of area up on the top and bottom a long distance away from the x-axis. All right, so that's why it has a big moment of inertia. Okay, so likewise the y-axis here. So the y-axis, we can find the moment of inertia about the y-axis as well. So that's the distance that it is away, the area is away in the x direction. Okay, so let's do an example here of the calculus form of finding the moment of inertia. Okay, so we have this rectangle. Let me scale this down a little bit. And let's just say we're trying to find the moment of inertia about the x-axis here. So what we want to do is integrate the area in terms of y squared dA. All right. So what we have here is our differential element. You can think of this as dA, just a small bit, the d meaning small bit of A. And the height of this rectangle is dy, right? It's dy. And the width of this rectangle is, if this is b over 2 and this is b over 2, the width of that is b, right? The width of that rectangle is b. So we have our differential area, dA, is equal to b dy, all right? B being the length, dy being the height. Okay, and y, the distance this differential element is acting away, right, is y, right? So the distance that is away is our distance y here. Okay, so let's integrate that. So if we're doing y squared dA, let's just write out dA there. So dA becomes b dy, right? That's our dA. And so we're integrating about y here. So where do we want to integrate from in the y direction? Well, we have negative h over 2 to h over 2. All right, so we're integrating from this point down here, which is negative h over 2 in the y direction, all the way up to h over 2. So let's do this integration. So y squared then becomes, so b is a constant here. So we can pull b outside. So we have the integration from negative h over 2 to h over 2, y squared dy. Integrating that, we have y cubed divided by 3, right? That's the integration there. And remember to put the b out front because that's a constant. And we are evaluating this from negative h over 2 to h over 2. All right, so what's that come out to be? Well, let's follow the calculations out. We have b out front. H over 2 cubed turns out to be h cubed over 2 cubed, and that's all over 3. And then we have minus a negative here because it's negative h over 2, which turns into a plus. We have h cubed over 2 cubed divided by 3. You might need to work this out on your own just so you believe me. All right, let's keep going. And that is... that simplifies to h cubed. This is 8 times 3. That's 24. H cubed over 24 plus h cubed over 24. And we can't forget the b out front. And that then simplifies 1/24 plus 1/24 is 1/12 bh cubed. All right, so the moment of inertia about the x-axis is 1/12 bh cubed. Now, if we note this on this diagram here, the x-axis is, and the y-axis for that is going through the centroid. Now, oftentimes we use the notation, if the axis goes through the centroid, we put this line over top of it. Remember, for the centroid of an area, remember we talked about putting a line over top of the letters x and y to indicate the centroid. The same thing for the moment of inertia. So this is the moment of inertia about the x-axis here through the centroid. And that is the solution we get. Now, this would be a real pain if we had to calculate this using differential equations every time we wanted a moment of inertia. Okay. With that being said, the back of the book has the moment of inertia for some common shapes, and I've listed these here. And as you see, things like circles, semicircles. Now, we were using a rectangle here, and the moment of inertia about the x-axis here is 1/12 bh cubed, exactly what we found. And if we want the moment of inertia about the y-axis, it's just 1/12 hb cubed. So these variables are just swapped here. Okay, so that is the way to find the moment of inertia about a centroid axis.